This video is about the fundamental theorem of calculus, part 1, sometimes abbreviated as FTC1. And I will say that different textbook authors sometimes categorize these differently. I've seen various authors maybe not call this part 1. There are some different ways to contextualize it, but as we finally get to the end of it, including part 2, you will see how it all fits together. For our notes, we'll say this: let f of x be a continuous function on the closed interval from a to b, and we're going to define a new function here. Now, this is usually, I think, held well on a picture, so we're going to draw a quadrant 1 picture here with a smooth curve just kind of floating through it, which happens to have, the way I've drawn this one, a peak and a valley. It just kind of goes up and then down and then just continues with an end behavior going up. This curve will just help us illustrate this definition. Now we're going to name this curve f of t, and in so doing we're going to call what we typically think of the x-axis as the t-axis. Now you'll notice in this function we're about to define here a couple different variables being used, and so that can be confusing. But hopefully by the time we're through this explanation it'll make some sense. This new function which we're going to define as g of x is as follows. It's the definite integral from a to x of f of t dt. So now you can see why it might make sense for us to have f of t shown in our picture. Now, on this closed interval from a to b, let's go ahead and mark that by putting a and b on our t-axis. Those will just serve as some boundaries for this function, a on the left, b on the right. And then we're going to find a place somewhere between a and b to mark and call that place x, the value x. So in other words, x is some value on this axis between a and b. Now at x, I'm going to put a vertical dashed line going up to the function just to understand where it is vertically here. And then if we understand what we already know about definite integrals and how we've discussed area under a curve, we could, just for simplicity, understand that in this picture where we have a positive function. So this f of t function is above the t-axis. You could say it's where f of t is greater than or equal to 0, which is the kind of function we used when describing area under a curve. And as we saw in the definition of the definite integral, the limit definition that is, the definite integral can represent the area under a curve in the case where the function is positive. So we could say that this definite integral we're seeing in our g of x function, that is the definite integral from a to x, notice we have a and x in our illustration, a being the left boundary of this closed interval, and then x being some value within the interval. This definite integral could represent the area under this curve from a to x, if you consider those as the bounds of the integral. Which means we could say that in this picture, g of x is really simply the area under the curve from a to x. I'll just shade that in a blue color here to help us understand, at least graphically here, what this definite integral could represent. In other words, that's what g of x is or could be here. Now, it could be slightly confusing to have the x and the t playing in the same playground here on this graph. Normally we're used to the x-axis, although sometimes we do use t instead of x as the independent variable. But in this case, we actually have both. So what's going on with that? Well, if we understand g of x, so g now is a function of x, and we understand x to be a value between a and b, then let's think of how this g of x function could depend on x. If we understand g of x as the area under the curve from a to x, as I've shaded in here, then really that area could vary depending on where x is, right? If I let x kind of slide down the axis, maybe closer to b, then that area region would grow. It would be expanding to the right. Or if I, on the other side, moved x closer to a, then I would be using less of a space between a and b under the curve for this area function g of x. In other words, sometimes this function is known as the area so far. That's not a very formal understanding, but it's a descriptive understanding where if I were to let x be somewhere between a and b, then g of x is really the area so far from a to x. Now let's continue to build on this function idea of g of x, the area so far. Again, so far referring to wherever x is in the interval from a to b. Now let's recall the limit definition of a derivative given this g of x function we've now defined above. We could say g prime of x is equal to the limit as, I'm going to use a variable delta x here, approaches 0. Sometimes we use the limit as h approaches 0. I'm choosing to use delta x in this context, but it's really the same thing. It's just some variable. So we want the limit as delta x approaches 0 of this difference quotient, as you may recall. So now we're using the g for our function. So we have g of x plus delta x minus g of x all over delta x. This is just the limit definition of the derivative that we've done now for a while. Instead of h, we're using delta x, and we're using g for our function name here. But that's all this is. Now let's go back to our diagram to understand what this could mean. Remember, delta x, just like h was when we were using that, is just some very small, arbitrarily small value. And if I add it to x, then I could say that, I have a place already on my diagram where x was, and it's between a and b. If I have x plus delta x, then that's just a little further down the axis from it, just slightly further down. And the reason that may be relevant is because as part of this difference quotient now we have g of x plus delta x. Now in our diagram where x plus delta x is, I'm going to add in another vertical dashed line segment just to kind of mark where that would be all the way up to our function, our f of t function of curve. If we understand g of x as defined above to be the area so far, that is the area from a to x, then we could say that the numerator of this limit definition of the derivative, that is the g of x plus delta x minus g of x, would be the area piece or portion between x and x plus delta x. Let's think about that for a second. G of x plus delta x would be the area from a all the way up to x plus delta x. So that's the g of x plus delta x, but then you're subtracting g of x, which would be taking away the area from a to x. So it's like taking away all the area before x, which leaves you with just this sliver in between of x and x plus delta x. So the numerator of this difference quotient as part of the limit definition of our derivative really represents the area between x and x plus delta x, vertically speaking, in this graph. Remember, the area idea here is just convenient for illustration, and we're assuming that this f of t function is positive here, which isn't always the case, but this is fine for the illustration and understanding this theorem. Now let's extend some algebraic work here with this g prime of x function we have. I could rewrite this by saying g prime of x equals the limit as delta x approaches 0. That's what we've already started doing here. But now I'm just going to do a little separation that I think will help understand what's going on. Instead of this numerator, which we've now circled in red, corresponding to the area shaded in red in our diagram, which is the area between x and x plus delta x underneath our curve. If I were to split this up and call it 1 over delta x times that g of x plus delta x minus g of x. Okay, so I'm just doing the algebra of fractions here, right? If I were to multiply these two algebraic terms together, of course that second factor could be over 1, then I would get really the same thing we had in the previous step. But we still have this area region represented, that is the g of x plus delta x minus g of x. It's the same thing we just had in the previous step that is shaded in our diagram. Continuing with this notation we have going so far, we could say that for small delta x, of course, small is a relative term, so we'll have to be a little more careful with that. But for small delta x, let's think about what's happening here. G of x plus delta x minus g of x, okay, so we've been using that expression already. That's representing that little sliver of area under the curve between x and x plus delta x. But for these small delta x values, that area we could say is approximately delta x times f of x. Okay, now let's be clear about this. I think maybe a diagram, an extra diagram might help. I'll just draw one to the side here. If we go back to our picture and recognize where x is, and I'm just going to redraw a simplified here curve we have going above, that of course somewhere to the right of x we put a place for x plus delta x. And we're talking about right now the area between those two places. That's what we've been describing with this red region here, this g of x plus delta x minus g of x. But what this recent statement here is saying for small values of delta x is that the right side here, this delta x times f of x, which I'm going to draw on this additional diagram here, that would be like a base of delta x, that's the width of this little space from x to x plus delta x, times f of x. Now f of x, remember f is our curve, it was an f of t curve, so f of x would be the height of the curve at x. Well, if I use that height as the height of a rectangle and the base being from x to x plus delta x, then that's what this right side delta x times f of x, that's a base times height of this now light green rectangle I've drawn in our secondary picture here. The point is that when delta x is small enough, this rectangle with a simple height of f of x has an area that could represent the area under the curve from x to x plus delta x. There could be a little error in the way that this curve kind of bends, whereas this simplified rectangle doesn't, it's just straight across. But when delta x is small enough, we could say that that error is minimal enough not to matter, and we could say then that delta x times f of x could represent this area, this red area that we've been talking about now all the way down. So let's take this another step and combine two things into a better notation. When we said for small delta x, right, that's a fairly relative term, but we can talk about very, very small values with limits as things approach zero. We've been dealing with that. And furthermore, if I take this equation, or at least it's an approximate equation at this previous step here, and solve it for f of x by dividing both sides of it by this delta x value. Okay, so let's combine those two things and we'll get the following. We'll be able to say that the limit as delta x approaches zero, so that's talking about really, really small delta x values. Okay, the limit as g of x plus delta x minus g of x, which by the way is the left side of this previous step approximate equation here. But now if I divide both sides by the delta x on the right side of this approximate equation, then I would have a delta x underneath that difference of g of x plus delta x minus g of x. And we could say that that is approximately f of x coming from this previous step, this approximate equation. But if you string all these pieces together that we have going above, this difference quotient, the limit that we've now written here, the limit as delta x approaches zero of g of x plus delta x minus g of x all over delta x, as we defined that above, that's really just g prime of x. Now with the limit being introduced, as we've done here, we can change from approximately equal to just to equal to. The limit is what enables us to get so small with delta x that it becomes equal, as we've discussed here algebraically, which means we now have a very significant result. We're now saying that g prime of x is equal to f of x. You can connect the beginning and end of this equation algebraically. It's all tied together by the steps we've just shown, and it's saying g prime of x equals f of x. Now, this is a bigger deal than it probably seems to you at this point. What we're saying, and I'm going to put an exclamation point by this result at the end, just to kind of mark that this is a big deal. We're saying that we now found the derivative of g of x. That is g prime of x. This takes us to the definition of FTC1, that is the fundamental theorem of calculus part 1. If f is continuous on the closed interval from a to b, then g of x, defined as the definite integral from a to x of f of t dt, that's what we have above, where x is somewhere between a and b on this closed interval, like we have above, is continuous on the interval from a to b and differentiable on the open interval from a to b, and g prime of x equals f of x. One way to grasp the significance of this is to say that g of x would be the antiderivative of f of x. That would be consistent with this notation and what we've already discussed with antiderivatives. The reason that matters is because what we're really saying in this theorem is that any continuous function, that is f of x here, has an antiderivative, that would be g of x. Now, it's often the case that this is really not a big aha moment for students. You know, if you've been following this enough to connect the dots and actually believe it, you still may not be amazed by this. And so it really isn't until we get to the fundamental theorem part 2 where you'll finally see how this is usable to really simplify the rest of the theorem, which is much more practical and useful. Let's try some examples where we use part 1 of the fundamental theorem of calculus to find the derivative of the function. Now we're here defining, number 1, we're defining a function g of x as the definite integral from 1 to x of the natural log of 1 plus t squared dt. Now, as you'll notice above, this actually fits with the way we defined g of x. If you go back up to our notes, we defined g of x as a function, the definite integral from a to x of f of t dt. Well, in this case now in our example, we're giving f of t more specific definition, but we're still using the same scheme we defined above for g of x. In so doing, we can just kind of utilize everything we've talked about to say that g prime of x, which by the way is what we're trying to find here, the derivative of the function, right? Our function is g, our derivative then would be g prime. Well, what we just concluded in this demonstration of the part 1 FTC is that g prime of x is going to be f of x, which would simply be rewriting the function in this integrand, but with an x as its variable. So we have f of t defined here. This is f of t, that's the natural log of 1 plus t squared. So f of x is simply the natural log of 1 plus x squared. It almost seems too easy. We're just replacing t with x, but that's exactly what this theorem says works when we connect all these pieces together. Let's try a second example. This time the function is defined as r of y. Okay, so we're just throwing in some different letters here. But r of y equals the definite integral from y to 2 of t cubed times the sine of t dt. Now, you'll notice, obviously, there are some different letters being used. We have y as this independent variable instead of x. We have r instead of g, but it's the same kind of thing with one significant exception. That is, if you'll notice the bounds of this integral, they seem to be flipped. If you go back to the previous example, that function, the definite integral, went from 1 to x. If you go way back up to where we defined this g of x function, that definite integral went from a to x, of course, a being a real number there, and so we're replacing that with 1 for this first example. But notice these bounds seem to be reversed. We want the real number as the lower bound, or the lower limit, and the variable as the upper limit. Well, thankfully, we know some properties of definite integrals that could be used simply to flip those. As you may recall, if you simply put a negative sign out in front of a definite integral, you can flip the bounds, so that would put the 2 as the lower bound and the y as the upper bound. It wouldn't change anything else though, so we still have t cubed sine of t dt for our integral. But now we can go right with our theorem, the part 1 of fundamental theorem, which says, of course, we have f of t written here as t cubed times sine of t, and we know that r prime of y, so now we're saying the derivative of this function is simply going to be, well, we keep the negative that was out in front of our integral there because we had to put it there to switch the bounds, so we're going to keep it there in front, but now we're simply going to write r of y, where we'll get y cubed times the sine of y. And so there's our r prime of y value using this first part of the fundamental theorem. It seems simply like variable swapping, but if you understand the full context, it really does work. Let's try a third example. This one reads, h of x equals the definite integral from 1 to the square root of x of this function, which is a rational function having z squared in the numerator and then z to the fourth plus 1 in the denominator, and that is dz. So we are still using here the first part of the fundamental theorem, trying to find the derivative of this function defined as h of x. Now, let's recall a couple things. We want h prime of x ultimately for our answer, but this one has some extra considerations. So just for use, I'm going to recall that, remember with Leibniz notation, h prime of x is the same thing as dh dx. So we're just going to recall that that's true. It's a notation for derivatives. Notice that in this problem, the upper bound of the integral is not a simple x, it's the square root of x. So in order to make this actually fit the first part of our fundamental theorem, we're going to have to do a little substitution here. So we're going to say let, and we're just going to pick the most common substitution variable seemingly used, which is the letter u. We're going to say let u equal the square root of x. That is that upper bound. That's a little more complex than we'd like. The formula simply has an x, or a single variable up there. So we're going to do that, or at least make it that way by using just u instead of this square root of x. Now, that's going to pose a little extra complication here, though, because I can't just simply swap that and be good. I have to understand also that du dx, that is the derivative of u with respect to x. That's just the derivative of square root of x. We've done that for a while now. That would be 1 over 2 square root of x. Furthermore, we must note how this is all going to fit together. So we could say dh dx, which by the way is what we're trying to find here. That's our ultimate goal. That could be written, now this won't be obvious until you see it and probably maybe have to use it again, so just kind of bear with me here. But dh dx is really the same thing as dh du times du dx. If you think algebraically using this Leibniz notation, these du's would cancel, and then of course you'd be left with dh over dx, so it actually works. But we're going to have to use that fact here. So we could say here that h prime of x, which is really dh dx, as we've already stated above, could be equal to d dx, so the derivative with respect to x, of the function from 1 to the square root of x times z squared over z to the fourth plus 1 dz. So I haven't actually used our substitution yet. We're about to, but we're just getting the full context of this here, which is equal to, I could say d over du times du over dx of the integral, the definite integral from 1 to u. So okay, there goes our substitution now that we're using du's. So from 1 to u of, same old function inside here, we have z squared over z to the fourth plus 1, and that is dz. But then if we rewrite this, so let's keep this idea going, I'm going to keep the d over du out front, but this time I'm going to just swap the order of some things here. I'm going to put the definite integral directly next, so we have the integral from 1 to u that we just had in the previous step here, of z squared over z to the fourth plus 1 dz, but you may say, well, where did the du dx go? Well, we're putting that now, I'm just going to throw it on the end here. It's just a visual aid, okay? So that's going to have the same values as the previous step, but I've just kind of swapped the order of them. You may say, well, what's the point of that? Well, because now what we've actually created in the first part of what we have before this du dx at the end is an opportunity to use the FTC1, the fundamental theorem part 1. Notice now we have the integral from 1 to u, so it's a simple variable, that's the one we swapped out, of this z squared over z to the 4th plus 1 dz. Using that theorem, the first part, this would simply be u squared over u to the 4th plus 1. But now we have this extra du dx from that previous step that we really do have to bring down with us. Now that we've been able to use the fundamental theorem part 1, we want to go back and just kind of reverse our substitution here. We know that u, the letter u, was just used as a helper in this case when it really represents the square root of x. So if I go back and replace that, I really have the square root of x squared over the square root of x to the 4th plus 1. I'm just swapping out u for square root of x. But then du dx, we also computed above. If you recall, that was the 1 over 2 root x. So we can replace that as well. And just call that 1 over 2 root x at the end. This now is ultimately our answer, but let's simplify it a little bit. This could be rewritten as x over x squared plus 1 times 1 over 2 root x. Sometimes you may find people rationalizing an answer like this and not leaving it in quite that form. If you did so, you could end up with the square root of x over 2 times x squared plus 1 in parentheses as our final result. So this is a perhaps more complex example due to the fact that the upper bound on this original definite integral was not a simple variable. But in these cases, you can use a substitution. If you simply try this a couple times with a couple different examples, I think you'll find that the pieces do fit together and use this theorem to get the result.